Let's apply Coulomb's law to a challenge problem. So here first we can see that we have an x-axis on which there is a positive 2 millicoulomb, which is at the origin, and then there is negative 5 millicoulomb, which is located at a distance of 1 meter. So I'm going to name the two charges as Q1 and Q2. The question is asking where could a positive 7 millicoulomb charge be placed so that the net force on it is 0. So let's assume that is Q3, which is positive 7 millicoulomb, and it's asking the net force to be 0 on Q3. That means Q3 is in equilibrium. Now Q2 is greater than Q1, we can see that because 5 is greater than 2. So the magnitude of Q2 is greater than Q1. And we know that from Coulomb's law, force is directly proportional to the product of charge and inversely proportional to the distance between them. So right now we don't know where Q3 is placed, but we know that the charges are we know the value of the charges. So based on this information, we can justify and say that the force on the third charge because of the first charge will be less than the force on the third charge because of the second charge, because the second charge is having a higher magnitude. So the force applied by the second charge on the third charge would be of a greater value. Now we want to change so this means that Q3 should be placed closer to Q1 because we want to change this inequality into an equality sign. That means we want to make F31 equal to F32. And in order to do that, we have to place Q3 closer to Q1. Now let's divide the x-axis into 3 regions, first, second and third. Q3 cannot be in the third region because that means it is going to be closer to Q2, and we already said that it has to be closer to Q1. So the only places or only regions where Q3 can be is first and the second. Now let's assume that we are placing Q3 in the second region. Then the forces because of Q1 and Q2, both of them will be towards right. If you want to check one by one, Q3 is positive, Q1 is positive. That means there will be a force of repulsion. So we can see that F31 is towards right. Q2 is negative and Q3 is positive. So F32 will also be towards right because it will be an attractive force, and that means Q3 is being pulled towards right. So as the forces are in the same direction, we are going to add them, and that means a possibility of making them equal to 0. That means when you add and you get the number as 0 is not existing. You cannot get the net force in the second region as 0. That means our second region is also cancelled out. So now we are left with the first region. In the first region, again we will draw F31 and F32 based on the attractive and repulsive forces, and this time we see that F31 and F32 are in the opposite direction, and that's what we need because we want to see that the net force becomes equal to 0. So in the first region, we have a possibility of making the two forces F31 and F32 equal to each other, and as a result of which we can get the net force equal to 0. That means the only region where we can place Q3 is the first region. So now let's say that we place Q3 at a distance of x from the origin. Now we are going to redraw it, and we are going to generate an equation for it so that we can solve for x. So let me just rub this out. This is not required anymore. Okay, so now F31 is equal to F32 in region 1. So we can generate the equation using Coulomb's force formula, which is kq3q1 over r31 square equal to kq3q2 over r32 square. We can simplify this and we can get the equation in this simplified form. Again, recalling that we are equating the two forces because the question is telling us that the net force is equal to 0, which means the two forces must be equal to each other and opposite. So we have already seen that the forces are opposite to each other. Therefore, now we are equating it to get the value of x. Now we substitute the values which are given to us for Q1 and Q2. So Q1 is 2 millicoulomb. And then R31, we can see in the diagram it is x, so we can replace that. And Q2 is 5 millicoulomb. And R32, if you look at the diagram carefully, it is x plus 1, which we can substitute in the equation. And we can get an equation for x, which we can solve to get the value of x. Now, one thing which you can notice here, that I have substituted 5 as positive, though 5 is negative, but I'm substituting 5 as positive. The reason is that the negative of the charge has already been considered while checking the directions of the forces. If you remember in the previous slide, we already took into consideration the negative of the charges and the positive of the charges to get the direction of the forces. So when we substitute, so let's go back, when we substitute it in the equation, we don't have to put the negative of the charges, and we can generate the equation to solve for x. Now the rest is mathematics, so I'm just going to rearrange the equation and get the final answer for x. So here it's a quadratic, so I'm using the quadratic formula. You can use calculator to get the value of x. I get it as 1.732. Okay, and I can see that position of Q3, because it's on the negative side of the x-axis, the value will be negative 1.7 meter.